Okay, so today we're going to discuss RRAM, one of the non-volatile memories. And this is the outline of today's lecture. So first we will give a brief introduction to the RRAM, and then we will go over the device properties from the representative samples. One is from E-tree, the other is from IMAC. And then we will discuss the physical mechanisms of the RRAM operations. And then we will show the array level integration strategies, and then we will showcase some of the chip level demonstrations. And finally, if we have time, then we will briefly discuss the 3D vertical RRAM concept. So RRAM is short for resistive random access memory. And RRAM has two subcategories actually. So the first one is this oxygen vacancy based RRAM, or sometimes we can do it as OXRAM. So in this OXRAM, so the device structure is a 3 layers of stack. It's a 2-terminal device. So you have 2 electrodes, top electrode and bottom electrode. Those are typically metallic electrode. And in between, there will be oxide, metal oxide. So the RRAM device relies on the formation of this filament made of the oxygen vacancies. So if you have the filament, then you store state 1, and if you don't have the filament, you store state 0. And the second category of this RRAM is called this CBRAM, conductive bridge random access memory. So this one is based on the metal ion migration into the so-called solid electrolyte material. This could be oxide or could be chalcogenide. So here the physical mechanism is still based on the filament, but the filament composition is different. So in this case, we have the active electrode, and typically it's made of like copper or silver. So copper and silver atoms can be easily ionized. If you apply positive voltage, they will become like copper ion or silver ion. So they can diffuse into the insulation layer and form this metallic filament to conduct the current. So there are 2 subcategories in the RRAM devices. And today we are going to focus more on the OXRAM, because this is more widely used in industry today. So this RRAM Basics, we already briefly discussed that. You have 2-terminal device. It's a resistor, essentially. Right? It's a resistor. And if you apply ground voltage to the bottom electrode as a reference, and then the external voltage is applied to the top, then we can do this so-called double sweep for the current versus the voltage, this IV curve. So you start with 0 voltage and then apply positive voltage, and then after some threshold voltage, then the device can switch from the high run state, HRS, to the low run state. So you have abrupt jump of the current at this moment. So the switching happened at this voltage. And then after that, typically we need to apply a set compliance current to limit the maximum current that flows through the device. And this is enforced either by equipment or by the series transistor. And then we sweep back, then the device is kept at the LRS, even the voltage returns to 0. If we want to reset the device, then the bipolar operation, we have to apply negative voltage here. And then after a certain negative voltage, the device progressively decrease the current. That means higher resistance. So here, then after like negative 3.3 volt sweeping, then we gradually reduce the negative voltage. Then the device will return to this high-run state. So here, the definition, like a 0 state is a high-run state, is off state, and the 1 state is a low-run state, and it's on state. So typically, we call the HRS to LRS switching, this side, as a set process. And then the LRS to the HRS switching is called the reset process. Actually, the IV curve we show on this plot is taken from one of the devices I made in the Stanford clean room, like more than 10 years ago when I was a student. So my PhD thesis was on this oxide RRAM device physics. All right, so then the other subcategory is called this conductive bridge random access memory. So in this case, here we show the 3 layers, and we tilt this by 90 degrees. So the device, let's say the top electrode is on the left, bottom electrode is on the right. And so here the idea is that one of the electrode is active because in this case we have the saver, or you can have copper. So when you apply positive voltage to the saver, so the saver will become ionized, then become saver plus ion. And then this positive voltage will drive the ion to diffuse into this so-called solid electrolyte material. And it could be oxide or nitride or even other chalcogenide or other even polymers. So basically, this electrolyte will allow the ions to diffuse. And when the saver ion reach to the other electrode, and typically this is called inert electrode, then the ion will be reduced to the atom. So you will deposit the saver on the other side. So you will gradually accumulate the saver. And then at certain points, then you grow this filament from the other side. And then once the filament touch, or let's say collect 2 electrodes, then the current will substantially increase. So this is like set process. And then if we sweep back on the elective side, so if you apply elective voltage to the saver, then here those ions, because they are positive charged, they will be attracted back towards the saver side. That means this filament will dissolve, and then if the filament completely dissolves, then you return to the original high resonance state. So here in this lecture, let's focus more on the oxide run, which is based on the oxygen vacancies to form the filaments. And even back in 2012, I helped my PhD advisor, Professor Wang, to write this review article published in the Proceedings of the IEEE, which I believe today has been cited more than 2,000 times. So even at that time, we summarized the material choices for the oxide RRAM. So basically here in the periodic table, the yellow color represents the binary oxide which has been reported to show this kind of resistive switching behavior. For example, those oxides like chrome oxide or iron oxide or cobalt oxide, So all of those metal oxide has been showing this resistive switching behavior. So you can say most of the periodic table in the metal element region, we can have those oxide, metal oxide, to show the resistive switching. And then blue color here is used for the electrode material, like the platinum, or sometimes, as we see earlier, the silver and copper for the electrode. And here I highlight a few elements in red circle. The reason is that after the material screening by the research community, industry focused on those elements like hafnium oxide, tantalum oxide, zirconium oxide, or the aluminum oxide. The reason is that those materials have been already used in the CMOS fabrication, so they are compatible with today's foundry process. Like hafnium oxide, foundry already use that for the high-k metal gate. Zirconium oxide, we already use that for like high capacitance, for example, in the DRAM manufacturing. So those are more friendly to the industry. That's why those materials stand out, and also their properties are generally good in terms of the memory characteristics. So next, let's have a summary of the key attributes of the RRAM devices as a memory. And here, a typical read and write speed to switch from high to low, low to high resistance could be as low as 10 nanoseconds, and sometimes you may need like hundreds of nanoseconds. But the state of the art can be less than 10 nanoseconds. And typical programming voltage, this is write voltage, the V-write, needs like 1 to 3 volts. This is higher than the logic VDD, like your SRAM needs only less than 1 volt. But this one needs a little bit higher voltage, typically on the range of the I/O voltage, but it's lower than the flash, flash more than 10 volts. And the programming current, this is the write current to switch the device, typically 1 to 100 microamp, let's say tens of microamp to 100 microamp. So this is still a little bit large because the minimal transistor, let's say W over L equals to 1, may only deliver like 10 microamp or 20 microamp. If your programming current is like 100 microamp, then you have to size up the transistor for this 1T1R structure as we discussed before. Cycling endurance, how many times you can write the data into the device. And it has a wide range reported in the literature, typically like 10 to the power 6, and the best reported number is like 10 to the power 12. But I would say most of the devices is on the lower end, like 10 to the power 6. And retention, and through this Arrhenius plot, like this 1 over KT plot, you can extrapolate that, and many devices can sustain more than 10 years at 85 degrees C. Scalability, so the single RRAM devices have been scaled less than 10 nanometer in the dimension. So the scalability of the device itself is not a problem. And the layout area is majorly limited by the series transistor. And as I just mentioned, the material set compatible with CMOS, like those aluminum, hafnium, zirconium, tantalum, those are widely used in the CMOS foundries today. And the fabrication temperature is less than 300 degrees C, typically by the sputtering or mostly by the atomic layer deposition, ALD. So this is compatible with so-called back-end of the line fabrication. Back-end of the line means the interconnect level fabrication. we have the thermal budget, typically 400 degrees C. After you fabricate the transistor on the bottom, then you do the interconnect on the top. When you do the interconnect on the top, the maximum temperature for the fabrication is about 400 C. This is to prevent the melting of the interconnect underneath, and also is to prevent the degradation of the transistor performance. Because if the temperature is too high, then the transistor which you prefabricated underneath will suffer from the degradation. But this RRAM can be deposited at lower than 300 degrees C temperature, so it's not a big problem to stack the RRAM on top of the interconnect. So let's, before we move on, let's see if we have any questions so far. So there's one question from the chat. Is there any significance reporting retention at 85 degrees instead of room temperature? Okay, that's a good question. So the 85 degrees C is an important number for the memory or industry, because this is like an industry standard for the like retention spec, because you need to account for the operational temperature of the chip at some extreme conditions. Right? So when you operate your chip, you have the self-heating, and then you have to make sure the device can sustain the retention at higher temperature at 85 degrees. So this is a conservative design spec. And then let's go back. In the next, we are going to show some device properties from two representative samples from the EFlash or the IMAC. And EFlash is the Industry Technology Research Institute in Taiwan, and it's one of the pioneers who developed the RRAM technology. And back in 2008, EFlash was the first to report the hafnium oxide-based RRAM technology, and this device structure has been later transferred to many other companies, including today's TSMC. They use similar stack as this one. And here, this is 1T1R schematic, and the RRAM is integrated as the via, contact via of the drain of the transistor. And in this stack, the oxide layer is the hafnium oxide, and then we have the top electrode, which is a combination of the tinitride and Ti, and then the bottom is the tinitride. Again, the tinitride is the conducting. It's one of the popular electrode materials in the fabrication. And here is the zoom-in image under the microscope. This is a TEM. And here you see that this diameter of this device is like 30 nanometer, and thickness of the hafnium oxide is only like 5 nanometer or so. And here we have some so-called capping layer. This Ti is called capping layer. The purpose to have some metallic layer is to have the oxygen gathering effect. So basically, this metallic Ti can extract the oxygen from the hafnium oxide to the titanium layer. Therefore, the hafnium oxide, so here the composition is less the stoichiometry. So that means it's not hafnium oxide O2, it's not HFO2, it's HFOX. The reason is that some of the oxygen extracted to the Ti layer, so the X is smaller than 2. So here we intentionally create some defects or oxygen vacancies in the hafnium oxide by this capping layer. And this is a common strategy in the RRAM device structure design. Okay, so this 1T1R structure, and then if you measure the IV characteristics, so here is the typical double sweep as we showed earlier. So you can apply the voltage to the bit line, that means to here. Then you will see this double sweep and the set voltage, reset voltage, and here the compliance, the current compliance could be modulated by the transistor's gate voltage, because here you have the gate voltage to this transistor. So then this transistor gate voltage, if you increase the gate voltage, you allow more current flowing through. If you use that as the compliance current, then you can limit what is the maximum current you flow through the RRAM device. So the gate voltage in this case is the tuning knob to determine the current level in the low resistance state. And on the right hand side, we show the cycling endurance for this device. So typically the cycling endurance testing is a repetitive like a set and reset sequence. So you apply typically like let's say a positive pulse, like 1.5 volt in this case. And then you read the resistance, and then you monitor this resistance here. And then you apply a negative, in this case, negative 1.4 volt pulse. And after that, you read the resistance. Then you record the resistance here. So this is like a pair of the set and reset. And then you can get these 2 points. And if you keep doing that over the cycles, then you will see the endurance evolution over the cycling. And in this case, you see that the low resistance state is pretty stable, but the high resistance state tends to decrease the resistance. So you do see the on-off ratio reduced after the 10 to the power 6 cycles. And if you have a reference in the middle, then if this, go across the reference, that means a failure of the cell. And also here, the switching speed can be monitored by shrinking this pulse width applied to the cell. So here there are some sophisticated test setup to apply less than 1 nanosecond pulse to the device. Because below 1 nanosecond, you have to really deal with those prosthetics in the testing setup. And here, if you do that by compensating the prosthetics through the transmission line, then here the smallest switching can occur at 300 picoseconds. So that means here you can switch the device 300 picoseconds, 0.3 nanoseconds. So it could be pretty fast. And then data retention, typically we bake the samples at high temperature, for example here 150 C, and then we monitor the resistance over the time. And here typically the time scale, for example 10 to the power 4 second is about 3 hours, 10 to the power 5 is about 1 day here. And here we care about this number, 3 times 10 to the power 8 seconds. This is about 10 years. Of course, here they just measure the resistance at one temperature and then do the extrapolation. Say this is safe for 10 years. But this is not a good extrapolation. Why is that? Any idea? Because here you only test up to 1 day, and after that you don't know, right? Maybe the device will suddenly fail like this. So it's not accurate to do this kind of simple extrapolation. What you should do is to do this Arrhenius plot 1 over KT, right, as you have done in your homework. So you need to test until you see the failure. and record the time. So for example here, if it fails here, right? So let's say you record is 10 to the power 6 seconds at 150 degrees C, and then you vary the temperature, maybe 200 C it will fail earlier, at 10 to the power 4 seconds at 200 C. So with those points, you of course vary the temperature in more steps, so you can get a few more points in the 1/kT plot, and then you do a linear fitting to extrapolate to lower temperature and for 10 years, as you have done that in homework. Next, this device also can support the multi-level cell. And there are two methods to achieve multi-level cell. So multi-level in this case means different resistance. So here you can vary the reset voltage. So when you do the elective sweep, you can stop at different negative voltage. For example, here negative 0.8, negative 1.1, or negative 1.4. Then you will get different states here. Or in the set process, you can vary the compliance current. As I just discussed, you can change the gate voltage of that transistor to change the compliance current. For example, if the compliance is 23 microamp, then you get this state. If it's 134 microamp, you get this state. If 400 microamp, you get this state. So you have different levels in either the set or the reset process. And after you get different levels by varying those programming conditions, either the set or the reset, then you can get those multi-level resistance states. And as you know, if you want to encode 2-bit data, you need 4 levels, right? If you need 3-bit data, you need 8 levels. And then you care about the retention of those multi-level states, and then you still bake that, and hopefully the multi-level states will not overlap, and then you can get reliable multi-level states. Any questions so far? Next, we will discuss the device from IMAC. And IMAC is a research institution in Belgium, Europe, and actually is one of the most advanced semiconductor research institution in the world. And many companies are member of the IMAC, like Intel, TSMC, they also support the IMAC research. So at 2011, IMAC reported a 10 nanometer hafnium oxide 1T1R RRAM device. So this is to prove the scalability of the RRAM device below 10 nanometer by 10 nanometer. And the device structure is similar as EFlash device reported earlier. The only difference is that in the IMAC stack, they change the high capping layer to hafnium capping layer. So in their device structure, oops. So they top ti nitride, and then this capping layer become hafnium oxide, and then you have the hafnium oxide. Sorry, this capping layer become hafnium metal, and then you have hafnium oxide, and then bottom ti nitride. So this is a similar structure as the EFlash structure. And here they made a very small device, 10 nanometer by 10 nanometer. So here this is a cross point like structure. You have the top electrode, bottom electrode, and the cross point here, the dimension is like 10 nanometer by 10 nanometer. This is one of the smallest devices made today. And here we have the cross-sectional view of this device. You cut from either this this direction, or you cut from this direction, then you get those cross-sectional images. And you see those numbers, those are in nanometer, 10 nanometer. And the other side, this side is also 10 nanometer. So it's a very small device. But the transistor they use in this case is a 65 nanometer transistor. But the RRAM device is made on top with very small dimensions. And they have done some categorization of this device. And the first thing is that they look at the so-called forming voltage. So forming is the first step to initiate the RRAM switching. So typically in the RRAM device, the first time programming is higher voltage. And then in the following switching, you can use lower voltage. I mean higher voltage typically like 3 volts, lower voltage maybe 1 or 2 volts. So here they measured the forming voltage as a function of the device area up to this 10 nanometer by 10 nanometer sample, which you may need higher voltage for the first time. And depending on the thickness of the hafnium oxide, like 10 nanometer thick or 5 nanometer thick, if you do 5 nanometer thick, you can still form it with 2.5 volts. And also they found that the forming voltage is a function of the hafnium metallic capping layer thickness. If you have thicker hafnium then you can get more oxygen from the hafnium oxide. Therefore, the forming voltage can be lowered to like 1.8 volts. Oh, sorry, I interpreted this wrong. So the capping thickness either 3 nanometer or 10 nanometer. If you have 10 nanometer thicker capping layer, you get more oxygen, then you get lower forming voltage. And here those two dimensions are the device dimension, like 40 nanometer by 40 nanometer, or 1 micron by 1 micron. And after the first time forming, then the following set and reset voltage can be lower. So here across multiple device dimensions, even down to 10 nanometer by 10 nanometer, you see that the reset voltage is about 0.6 volts, and then the set voltage in their case is about 0.5 volts. And also the on and off resistance, they show the current, on and off current, like 10 microamp for the on state, like below like microamp for the off state. On-off ratio is like 10 in this case. So this is also independent of the device area. So here, the low significant area dependence suggests the filamentary mechanism. What does that mean? So that means no matter it's a large device or small device, the smallest here is like 10 by 10 nanometer, right? 10 nanometer by 10 nanometer, or here the large device is 1 micrometer. So no matter what size the device is, so let's say this, you have a small device, you have a large device, the on and off current is similar. That means the actual conductive region is very small. It's below even 10 nanometer by 10 nanometer dimension, maybe only a few nanometer by a few nanometer. So that means those are the filaments. Let's say you have those filaments. So that means no matter it's a large sample or a small sample, the actual conductive region is a filament. It's only with a few nanometer by a few nanometer like that dimension. Even you have micrometer like sample, only a very small portion is conducting. So that's why you change the area of the device, still the current is kind of similar. Or you can think the other way. If this is a uniform conduction, let's say the current flow everywhere, that means the current will be proportional to the area of the device, right? As Ohm's law suggests you. But in fact, the current is independent of the area. So that suggests the conduction is very localized to those certain filament regions. And also, the IMAC people have tested the relationship between the set and reset voltage and set and reset pulse duration. So it's a pulse amplitude versus pulse width. For the, I believe this side is the set process. The other side is for the reset process. So you do have some trade-offs here. For example, in the 10 nanometer sample. So if you want to reset, here this is like 10 nanosecond. You need to apply larger voltage, like 2.5 volts. If you relax your reset pulse to 1 microsecond, then you only need to apply 2 volts. So here you see the different combinations. Like 2.5 volts, you need 10 nanosecond. 2 volts, you need 1 microsecond. So there's a trade-off. If you want to operate faster, you have to apply larger voltage. This is easy to be understood because if you want to switch fast, then you need to apply higher voltage to drive those oxygen vacancy formation and migration. And also, IMAC tested the endurance of the device, and they found out that endurance degradation is a function of the programming condition. So here we show this resistance as a function of endurance cycles. And then here, depending on the set and reset pulse amplitude, for example here, we gradually make the set, this is the set word line. Actually, that means the gate voltage Vg to the transistor. That is this is word line, right? Word line controls the Vg. This is a set WL voltage, and then you have the resistor. So you make the Vg larger. That means you pass the current, complex current, larger. So here the reset condition is fixed to be 1.8 volts. But the set complex current gradually increase. You see that if the set is weak initially, the failure mode is they stuck at high resistance state because the set condition is weak. But as you increase the set condition strength, for example, to 1.4 volts, you see the failure mode is that the device stuck at the low resistance state. So here initially you're stuck with high resistance state because the set condition is weak and reset is stronger. So gradually then the device tends to move towards the high resistance state. But if you change the set condition to be stronger than the reset, relatively speaking, then the device stuck at the LRS. So if you optimize the set and reset conditions to have a balanced condition, then you can achieve like more than 10 to the 10 cycles as shown here with optimized set and reset conditions. And also IMAC tested the retention using the temperature accelerated testing. And this is what we suggested for the retention, right? So here at different temperature, for example, 250C, 200C, 150C, they measure how the low resistance state and high resistance state current change over time. And then the general trend is that both low and high resistance states current decrease, or in other words, resistance increase. So here you need to define the reference current, in this case, IRF. And then the hydrogen state become even lower current, so it's not a big problem. So the problem is when the low-run state current decrease across this reference, then you see a failure, and you record the time. And then this is how you get those points in the 1/kT plot. Time to failure. And then here we have two states because you can have multi-level states. One is a stronger lower resistance state. Typically the rate current is 100 microamp. And then the other one is a weaker low-run state. Rate of current is 10 microamp. But they have a similar kind of tendency here. So you have three temperature, 200, 250, 200, and 150, and then you do extrapolation using the 1/kT. And again, this is in the electrode volts. You have to convert that to the electron volt unit. And then you do that extrapolation. You see that it can sustain like more than 10 years at 85 degrees C. And the slope is the activation energy. It's about 1.2 to 1.5 electron volts. All right, any questions after we go through those sample examples? What is actually changing? Yes, so the E-tree use titanium as a capping layer, IMAC use hafnium as a capping layer. So according to IMAC, they think that hafnium can be more compatible because it's hafnium oxide and hafnium, so it can get more oxygen from hafnium oxide. But titanium is also very active, I would say. So I don't know exactly what, for example, later like TSMC or Intel use. They didn't disclose the exact stack, but I believe it's similar to IMAC or E-tree. You have some capping layer. Maybe different companies will optimize that capping layer to different materials, but the concept is reported in those papers. Next, we will briefly discuss the physical mechanisms. And this is what we speculated, what happened in the oxide run. So initially you have some fresh sample, so you have this metal oxide, and it's more close to perfect state with less defect. So this forming process is really to create the oxygen vacancies. Of course, as I discussed earlier, you can have some capping layer to initially introduce some of the vacancies. But still, you may need larger voltage to trigger the switching at the first time. So here you apply positive voltage on the top electrode, and then the electric field across this oxide can be very large because this oxide layer is only like 5 nanometer or 10 nanometer. If you apply like 3 volts, then the field, electric field, is large enough to lock out the oxygen from the lattice. So oxygen will become ionized, become oxygen ion, which is oxygen -2, and oxygen ion, which is those like yellow dot here, will migrate towards the positively biased top electrode. And what is left behind is the circle. And the circle is oxygen vacancy, VO, oxygen vacancy. So this is like electron hole pair generation, right? So you get the electron and you left a hole. And this here you get an oxygen ion, then you left with the oxygen vacancy. So after the forming process, then here you create those vacancy-based filaments, and current can conduct through those vacancy. And then the oxygen ion are deposited at the top electrode, and then they will be discharged and become like oxygen layer. It's not oxygen layer. This will react with the top electrode or with this capping layer. For example, if the capping layer is high, that means this interface will become partially oxidized to partially dioxide as an interface because you get more oxygen here. And then if you reverse the voltage to reset, you have a negative voltage applied here. Then this negative voltage will drive those oxygen ion back because it's negative charge. So oxygen ion, those yellow dots, will migrate back, and then they will recombine with those vacancy. So that means the filament will be ruptured. But typically, you won't rupture the whole filament. You just need to rupture the rupture the interface of the filament, and then you can create this tunneling gap. Now the electrons will see a large gap to tunnel through, and the resistance will become higher. And then in the next cycle, then you apply positive voltage again, so you will recreate those oxygen ion and vacancies. So you will reform the filament, and you can complete this loop for many cycles. But as you can imagine, it's very hard to precisely control the shape of the filament during the formation and rupture process, because this is an atomic process. Next time, the filament may grow this way, right? So this will result in the variations from cycle to cycle, and this is one of the challenges of the RRAM circuit design. You have to deal with these variations from cycle to cycle. Every cycle, the filament is different in its shape. Then you will introduce the resistance variation from cycle to cycle. And in the next, I will quickly go through some experiments to verify this is a filament switching. I will speed up this part. So the first experiment done by IMAC is to basically, after you cycle the device, let's say set and reset, then they remove the top electrode and they remove this electrode material. And then you expose the surface of the hafnium oxide, and then they use a tip. It's called the conductive AFM, atomic force microscopy. It's a very precise tip to scan the surface of the hafnium oxide from the top. And then here, this is the current map after the scanning. So the fresh sample, you see that the red color means very low current, like 0 picoamp. So basically it's insulating. Fresh sample, you don't have any filament. And after set process, if you scan the surface, you see this localized region right here. This is high current, like 5 nanoamp compared to picoamp range. So here that means the filament is formed in this region. Oops. And then after reset, then you see this filament region kind of disappear. This means the filament is ruptured, and the residue filament only conduct like 30 picoamp as compared to the 5 nanoamp in the set condition. So this experiment verified the filament formation and rupture in this hafnium oxide RRAM device. And also, this paper looked at the cross-sectional view by the EOS, electron energy loss spectroscopy. So it basically have an element map of this region. It can look at the oxygen profile in this region. So in this region, after set, we see less hafnium oxide O2. That means less oxygen in this part. And then we see that in the hafnium, you have more like oxygen in the cathode layer. So this is an evidence that the oxygen transfer from the hafnium oxide to the cathode layer, hafnium. in this case. And this diameter of this region is about 15 nanometer in this case. It's a localized change in the oxygen profile. And the conduction mechanism of this through the filament is typically so-called the trap-assisted tunneling. And this is actually from one of my earlier paper, like 10 years ago. So there are many conduction passes possible for like two electrodes separated by the oxide. But if you have the oxygen vacancy, then the most probable path is through those stepstone for the electrons. So electrons will tunnel from the electrode to those oxygen vacancy, or we call trap, and then they will tunnel from trap to trap. So this is a trap-assisted tunneling mechanism, and similar as what we discussed earlier in the flash. And there are also simulations to visualize the process. So here is a paper that try to visualize the filament formation and the rupture process by the 3D atomic simulations. So here I believe the red dot as the oxygen vacancy. So you do have some initial vacancy as fabricated in the oxide, hafnium oxide layer. And then here in this case, they have the tie as a capping layer. And then after the set process, then you create many of those vacancies. So the red dots are located in this part. And also you create many of those blue dots, those are oxygen ion. And then after the set process, then the oxygen ion will accumulate at the interface. And then what is left behind is this filament region. So this is a 3D view of the forming process. And then they try to do the reset. After reset, the filament is ruptured. So in this part, the red dot become less. So the vacancy become less, and the filament is ruptured. And then in the next set cycle, this part is recollected. So you regrow the filament. But of course, there are debates in the literature. The rupture of the filament is near the bottom or near the top electrode is still under debate. But I personally think it's near the top electrode. Because when the oxygen ion migrate back, they will first rupture this part. But still, this is a hypothesis. There's no direct evidence to really image, or let's say really see where the filament is ruptured, because this is only like a few nanometer dimension. It's very hard to visualize under the microscope. All right, any questions about the mechanism? Next, we will talk about some array level integration strategy and the demonstrations on the chip level. And the RRAM major players, actually, the RRAM has triggered a research wave across the globe in the past, I would say, more than 15 years now. And many research groups have been working on the RRAM, and also many companies have invested in the RRAM development. So here I just list a partial. Here is just a partial list of the players. And in US, those companies have invested RRAM before. They may not be doing that right now. Maybe some of them give up, but some of them still continue. So let's look at some of the prototype chips reported in the major circuit conferences like ISCC. So this is one of the earliest demonstrations, again from ITRI, the institution from Taiwan. So this is a 4 megabit 1T1R array and reported in ISCC 2011. This is on the 180 nanometer process. And the device is exactly what we showed earlier, but they integrate into the array with the peripheral circuits like decoder, sense amplifier, and so on. And at the chip level, it can reach like 1 bit per cell operation with read and write time, about 8 nanoseconds, and 2 bit per cell read and write time is 160 nanoseconds. The reason is that they need to do this write and verify. Similar as the flash, you do the ISPP. Because of the variation, the resistance of those 4 levels may have overlap. So you have to program and then read and then reprogram to create the gap between those resistance levels. So you can encode 2-bit data into those 4 levels. And the 1T1R cell size in this case is 9.5 f squared. So it's pretty compact. And the endurance reported 10 to the power 10, and the retention they have tested 28 hours at 150 degrees C. And then in the ISCC 2012, Panasonic reported this tantalum oxide-based RRAM. And actually, this is a cross-point array, not 1T1R in this example. So they do have a bidirectional selector based on the silicon nitride. So here, this is a selector. It's this stack. Tantalum nitride is the electrode, and silicon nitride is like the toluene layer. So they do have this bidirectional exponential IV for the selector. And here we have the half bias skin. So you know the on-off ratio, let's say the nonlinearity is, in this case is 150. So compare the current between V and half V. So this is a 8 megabit 1S1R, or they call it diode, but actually it's a bidirectional diode, so it's 1S1R. Cross-point array. And again, the CMOS peripheral circuit is on 180 nanometer process. And this is a chip macro. Has 4 like bank, they call 4 planes, and then you have the peripheral circuits. So at the chip level, they achieved like more than 400 megabytes per second write throughput. So basically, they can parallelly write 64 bits, and each write cycle is 17 nanoseconds. This is tested at the chip level. And also, they did this 1/KT plot, and then the extrapolated retention time can meet like 10 years at 85 degrees C. And later, actually Panasonic has commercialized this technology, and they have embedded that into the microcontroller, MCU. And actually, I don't know if it's still available now, but at some time, a few years back, you can buy it from the website. So this is a first RRAM-based product you can buy from the market. So this application is a microcontroller embedded memory, embedded non-volatile memory from Panasonic. So the reason that those companies position RRAM as a replacement for the embedded non-volatile memory for the EFlash, basically, EFlash. So EFlash is widely used in microcontroller MCU to store the code. And typically you need a few megabytes for that. And here, for example, it compares the RRAM versus the EFlash based on the Sonos patch trap transistor. This is from the Cypress. And you see that the chip area can be reduced, and also the power, let's say the total write current, will be much lower because the flash, in this case, will be no flash. And no flash, you know, the write is using the hot channel hot electron. You have to inject a lot of current. So here, the other metrics are comparable, but the major benefit is a smaller chip size and much lower write power compared to the patch trap based EFlash. And next, in the ISCC 2013, SanDisk and Toshiba jointly published this cross-ponent array, and actually we have discussed this before in the array level design lecture. This is the 32 gigabit RRAM chip, and the RRAM half pitch is 24 nanometer, but the peripheral circuit is maybe at 180 or 130 nanometer, and we have shown this cross-sectional image before. So this is like a 3D exponent. You have two layers of the 1S1R structure. And since I have already discussed this one before, so I will skip this here. And ISCC 2014, Sony and Micron jointly published a CB-RAM RRAM chip. This is 1T1R chip. This is 1T1R array. And then they use the DRAM design rule. So they achieve like 6F square, very compact. And the half pitch is 27 nanometer load. And the density is 16 gigabit per chip. So this is one of the largest chip reported so far. And here are more parameters. I will skip the details. The read latency is about 2 microseconds. Write latency is about 10 microseconds. So still this is much slower compared to the single bit or single cell operation. So this is at the array level, at the chip level. So the latency is not as fast as we may expect from the cell level. Probably because of the variation, you have to do the read and write and verify. So at the array level, the latency slowed down in this case. But unfortunately, after the publication, the 32 gigabits from the SanDisk and 16 gigabits from Sony and Micron, after that, I believe those companies give up. The major reason is the variation or reliability from the product perspective. It's very hard to control. And the yield, reliability, variability are the major concerns to have those large capacity RRAM chip, like 16 gigabit or 32 gigabit. So those companies give up because originally their goal is to do the storage class memory, because at the gigabit level, right, like the 30x point. So you have the gigabit level non-volatile memory. That's the sweet spot for the storage class memory. But later they realized this may be too challenging to have the uniform behavior across like gigabit cells. So they give up. So what remains today for the RRAM is on the embedded side. This is typically megabyte level, embedded 1T1R RRAM. And the TSMC has reported the 40 nanometer RRAM process, 10 nanometer RRAM process at ISCC 2018. And the cell size is enlarged because it's for the embedded applications. and the 1T1R, the transistor size, is enlarged, and it's about 50 f square, and here is the distribution. So here the on-off ratio is pretty small in this case. I believe only like 2 or 3 in terms of the on-off ratio. And just one more note, TSMC actually commercialized this technology. You can do the tape out with TSMC basically with 40 nanometer process. They offer as one of the solutions for the embedded non-volatile memory at 40 nanometer node today. And actually, the customers are using TSMC's process to design the 40 nanometer RRAM today. Actually, my research group also has been granted the access to this particular technology. So actually, from our group, we have designed a few generations of this 40 nanometer RRAM process. And then Intel reported a 22 nanometer RRAM at ISSA 2019, I believe. So here, this is integrated on their 22 nanometer XFL process, the FinFET-based platform. And also it's 1T1R. And here, the RRAM is integrated still as a DRAMware. So this is a transistor, and this is RRAM. So the write time is like 10 microseconds, and here read time is pretty fast. But still, I believe this 1T1R, the cell area is pretty large. If I recall, this one is 60 f square or even 80 f square. Because here, even though the transistor is small, the RRAM dimension is larger at the back end. Also, here we have a layout for this Intel's RRAM design. So you will see that it has multiple fins to drive the RRAM for the write operation. It's like 4-fin process here. And then RRAM is integrated here. So you have the source line, bit line, and then the gate is this dummy poly. It's not poly, but it's gate basically. And then the cell size is 200, close to 300 by 200 nanometer. And you can convert that to f square, and you will see this is close to like 80 or even 90 f square. So here is a closer view of the RRAM. The transistor is pretty small, but the RRAM here, I believe, is actually is here between metal 7 and metal 8. So because it's in the back end, so the dimension is much relaxed. So you see the transistor, let's say, interconnect. The lower metals have smaller pitch, but higher metals will have a larger pitch. Closer view. This is nice TEM picture actually. Very clear. This is the RRAM layer. And this is the FinFET underneath. You have 4 fins to drive one RRAM cell in this case. So here we have a summary for the recent chip demonstrations for the embedded non-volatile memory. This targeted application is for the EFlash replacement for the embedded non-volatile memory. And here are the cell size. For TSMC, actually recently they also reported a 22 nanometer process in VLSI 2020. So I would say TSMC and Intel are on the same page now. in terms of the RRAM. And the TSMC has a little more compact cell size in terms of f square. And then here, not all the properties are reported, but you can refer to this table if you want to know the characteristics of those demonstrations from the leading companies here. Read can be pretty fast, typically a few nanoseconds. And lastly, if time permits, we can briefly talk about the 3D vertical RRAM. So similarly as the 3D NAND flash, we can do the 3D vertical RRAM. And the idea is to have this vertical electrode and make the RRAM as a sidewall. So the motivation is the same as the 3D vertical NAND flash to reduce the cost of the mask if you can share the mask. So here the conventional 3D exponents as used by Intel and Micron for the phase change memory. So you have to increase the number of masks as you increase the number of layers. But if you can do the vertical RRAM, then you can save the cost similarly as the 3D NAND flash. So the idea is very simple. Make the pinner, one of the electrode as a pinner. And if you can deposit the RRAM material oxide as the sidewall of this pinner, then you make the horizontal electrode. So the overlap region here is the RRAM layer. So here, for example, you can make the RRAM as a sidewall. The resistor is on the sidewall of this pinner. And there are some early demonstrations by Samsung and Macronix, a Taiwanese company. And also in my PhD thesis, I proposed this kind of 3D exponent array using the vertical RRAM with a shared plane. This is very similar as today's 3D NAND flash if you look at this schematic. Right? So the RRAM is on the sidewall of the pinner. So you have the inner electrode and then a core shell structure. The RRAM and hafnium oxide is a shell, and then you have the plain electrode. So you can have this kind of 3D structure. So you only use one lithography to define the pinner. Similarly as the 3D NAND flash, you have the 3D pinner, the NAND stream. And also IMAC proposed to have a slit, basically cut those wire lamps into slit. This is also very similar to today's 3D NAND flash. I'll skip the details. And the recent demonstrations in IDM 17, like 8 layers of the 3D vertical RRAM has been experimentally demonstrated. You look at the sidewall here, the RRAM, there are 8 resistors in parallel here on 8 layers. So here. All right, so let's have a summary. The near-term application for RRAM is to serve as embedded non-volatile memory with 1T1R array. And you see examples from Intel and TSMC at 22 nanometer. This is ready for volume production, and actually it's commercialized already. TSMC is offering the tape-out using the RRAM. And the long-term application is to serve that like the storage class memory, but we have to do the 3D vertical cross-corner array to reduce the cost. And selector is the key. How do you integrate the selector on the sidewall? The challenge. So this remains challenging, this long-term application. RRAM suffers from the device uniformity variability issue. So this is a major concern for industry and commercialization of the RRAM. And we need to further lower the reset current to sub 10 micron level. Then we can reduce the 1T1R transistor width. So you can minimize the cell area. And also further improve the reliability, endurance, for example, and also retention for the tail bits. And demonstrate good characteristics within the same material system and at array level. So this is the to-do list for the RRAM business. All right, any questions before we stop? If not, then we will stop here today. Thank you.